the source of all knowledge. It says that a hair is between 10 and 100 microns. And the amazing thing is that Erik's instruments are capable of analyzing chemical and isotopic compositions in spots that are smaller than 1/10 of a micron. So, you know, to this scales, a human hair looks like a log. So he's used these for a variety of approaches, from understanding volcanoes to, in this case, looking at water in the moon. Water is an interesting problem to geology, because I think most of you don't recognize that most rocks actually have several weight percent water in them. And you can't take them, squeeze them, and get it out, but it's there, and it does some amazing things to the properties of the material, from lowering the melting point of rock by hundreds of degrees to making it flow much easier. And so it has a huge role to play in geology. Erik's talk tonight is on water in the moon. We are all, as students in this field, taught that there is no water in the moon. Well, that's no longer true, and Erik will explain to you how he gets that information. Besides his academic degrees, Erik's won a number of awards. He's won the Young Investigator Awards of both the European Association of Geochemistry and the American Geophysical Union. He's a fellow of both the American Geophysical Union and the Geochemical Society. So it's my honor today to introduce Erik Hauri, talking about water in the moon's interior, truth and consequences.
Thanks, Rick. That was a very nice introduction, and thank you all for coming. Really looking forward to this few minutes of being able to share my enthusiasm and joy in working on this problem with you all. I'm, as you learned in the tour, if you were on the tour last time around, I'm a mass spectrometrist working with advanced instrumentation, and so like a lot of instruments, the basement is the best place because it's very stable and you get very good data, and so I'm a basement dweller. But I'm trying to take you through the tour of why I'm interested in the moon. So the moon, of course, has an outsized role in history and culture. It's one of the sort of celestial objects that ancient peoples were drawn to immediately. The oldest lunar calendars date from sometime between 15,000 and 30,000 years before the Common Era. The slide on the left shows the different phases of the moon carved into a piece of bone that was recovered from the upper Paleolithic segment in France, and you have cave paintings that are very similar, showing the phases of the moon that are of similar antiquity. And so it's been an object of interest and observation for a very long time. The moon has, of course, been an object of religious worship as well. You have ziggurats in the Middle East. This is a ziggurat of the Sumerian moon god in Ur, that's dated to about two millennium before the Common Era, located in Iraq. And of course, the Roman goddess Selene is the goddess of the moon, the Greek equivalent of the goddess of the moon is Lunar. She's the daughter of the Titans Hyperion and Thea, and sister of the sun god Helios and goddess of the dawn Eos. So Selene was regarded by the Greeks as the personification herself of the moon. And we can, I think, credit the moon with probably the first series of real scientific measurements. If science is really driven by the curiosity of the observer, then the moon may represent the birth of science itself. And the idea that the moon was perfectly smooth, or was not perfectly smooth, can be traced back to Democritus, an influential Greek philosopher who's sometimes credited with being the father of modern science. He speculated that the moon had lofty mountains and hollow valleys because of the variations in the reflectivity of shadows and things that he saw on the moon. And of course, the moon was the first object ever observed through a telescope. The first observation of the moon through a telescope has now been accurately ascribed to Thomas Harriot. He made this drawing on July 26th, 1609, the first known sketch of features on the lunar surface viewed through a telescope. And this happened about 6 months, actually, before Galileo made his own much better telescope and published his observations of the moon, but also Jupiter and its 4 moons. So these observations really were the first discoveries that ultimately led to the rejection of the geocentric theory of solar system revolution and the adaptation of the heliocentric theory, which is that everything revolves around the sun, first advocated by Copernicus in 1543. And the moon also has an outsized role in our own modern culture as well. Some of you may recognize this album cover by the rock and roll band Pink Floyd. The inspiration, of course, was The Dark Side of the Moon, and this was an album that remained in the Billboard Top 100 charts from the week it was the week it came out, March 1st, 1973, for a subsequent 741 weeks. It's an object of great inspiration and interest. But they did not. No, they did not. But of course, for our purposes, the really outsized discovery and sort of landmark thing that happened or associated with the moon, of course, was the moon landings. The moon remains the only extraterrestrial object walked upon by people. So this is a photo of Neil Armstrong reflected in the visor there, and Buzz Aldrin himself standing on the surface of the moon on July 20th, 1969, almost exactly 300 years to the day after the first telescopic observations of the moon. So the thing that we keep in mind, we have to keep in mind when working on lunar samples, is the tremendous cost associated with these samples. The Apollo missions from Apollo 11 to Apollo 17 returned 840 pounds of samples that are curated at NASA Johnson Space Center in Houston. And one of the central goals of that curation facility is to keep at least 50% of the samples in pristine condition. And NASA's definition of pristine condition means that it's never seen the air, the terrestrial air. So they're either sealed in the original containers that they were loaded in when they were first sampled on the moon, or they've been kept in a controlled atmosphere that keeps the common terrestrial air away from them. And something like only about 10% of these samples by weight have actually been worked on. So it's an enormous resource, but it's a very careful parsing of these samples. You have to write a very good justification for a proposal, which is reviewed by a committee of scientists that either give you the thumbs up or give you the thumbs down. If you get the thumbs up, you get a tiny, tiny piece. You have to make the most of it and record every gram of what happens to it. And so it's very careful. And this is, of course, because the Apollo missions cost in 1970s dollars roughly $25 billion. The 2014 equivalent today would be about $165, or about 1/4 of the cost of the 2008 Wall Street bailout. But there's also a human cost, of course. 3 lives were lost. 3 astronauts died in Apollo 1 out of 36. And so that's a 9% fatality rate, which is roughly 1 million times more dangerous than common modern air travel. So we keep these things in mind whenever we work on lunar samples, and are extremely careful and extremely fastidious whenever we do anything with a lunar sample. Okay, so this talk will be divided up into 3 parts. I'll tell you a little bit about water in the solar system and why it's important. Rick alluded to it, some of its properties. I'll tell you a little bit more about it. We're going to talk about lunar volcanic eruptions. These samples were generated by volcanoes on the moon. And that's a very interesting topic. And then the data on water in these volcanic eruptions and what it really means for the moon formation. Okay, so water in the solar system. Hydrogen is the most abundant element in the universe. 90% of all the atoms in the universe, or 75% of the mass, is hydrogen. And most of that is in stars. The 3rd most abundant element on the Earth's surface after silicon and oxygen is hydrogen. Water is obviously, on our planet, required for the sustenance of life. And as Rick alluded to, it has an influential role on planetary properties that are actually outsized in proportion to the size of hydrogen atom, which is essentially a proton. So the whole reason we have continental drift and plate tectonics on the Earth is because liquid water is stable at the Earth's surface. And Venus, which has a single plate, which is not moving at all, there is no liquid water stable on the surface of Venus. So that's a first-order difference in these two. 150 parts per million of water, which is less water than you have in a single breath, is enough water to decrease the viscosity or strength of rocks by a factor of 1,000. And that's because protons break bonds, like to lubricate bonds. 700 parts per million of water will drop the melting point of a typical rock in the Earth's interior by 300 degrees. So you will make volcanoes in the Earth where you have wet mantle in places that are cold enough that you would never expect melting to take place, and you would never expect volcanoes to occur at all. And those are commonly related to the presence of water. So in the solar system, we have have obviously a very large temperature gradient. Things are hottest close to the sun, and you get much cooler as you go away from the sun. Hydrogen-bearing compounds, therefore, also follow this temperature gradient, especially during the phase of planetary formation, when the Earth and its sister rocky planets and also the gas giant planets were all forming in the first few million years of solar system history. So this temperature gradient, as you get away from the sun, results in essentially a frost line or a snow line. So inside the snow line, the temperature is hot enough that you actually vaporize water, and it is stable only as a gas. But of course, the sun wants to push it away and cause freezing on the other side of the snow line. And so that's why at some distance between the asteroid belt and Jupiter is the current place where you have the frost line. It's why you have gas giants outside the snow line and rocky planets inside the snow line. And the large difference there is that most of the hydrogen is outside the snow line, and the planets on the inside of the snow line are very depleted in hydrogen. And that includes Earth and Mercury, Venus, and Mars. So the evolution of this snow line and what happens as bodies cross the snow line is really important, as you'll see, for the formation of the moon. So in the first few tens of millions of years of Earth formation, we had collisions of a lot of bodies, both inside and outside the snow line, but I'm going to focus mainly on the rocky planets inside the snow line. Okay, so here we have a movie from our own John Chambers, who's modeling this collision process among different objects in the inner part of the solar system. He has modeled this very extensively, and what I'm going to show you is essentially collisions between two populations of bodies. So this is what John Chambers has modeled. There's a series of bodies here that are about 1% the mass of the Earth, and a series of bodies here that are about 10% the mass of the Earth. And we have distance in the units which is referred to as astronomical units. Now, one astronomical unit is 93 million miles, or the distance from the Earth to the Sun. So 2 astronomical units is essentially close to or beyond the orbit of Mars. And Mercury is inside a half AU. Okay, so what will happen is as these bodies collide with each other, their mass will start to increase, and they will move vertically on this diagram. So the number of bodies will get smaller, and the masses will get higher. So let's watch what happens. Oops, no, we have to go back. Okay. There we go. Okay, so as the bodies in the lower part of the diagram collide, they bump up. You have some bigger collisions here that increase the mass by a factor of 2 or 3. And as you get higher and higher on this diagram, you start to have collisions between increasingly large bodies. And these collisions between large bodies are what are referred to as giant impacts. The collisions down here are less than giant, but as you get up here, you have a series of collisions that are almost inevitable. And any sort of conditions under which you run a model like this results in the planets forming inside of 2AU experiencing at least one, typically several giant impacts. And giant impacts are extremely energetic. I'm going to show you next a movie that was produced by NASA, which is sort of the artist's rendition of a giant impact. This is a collision between something that's about the size of Mercury and something that's about the size of the Moon. And the collision speed here is anywhere from 10 to 15 kilometers per second. And what you're seeing here is actually a process that happens in a matter of hours. So if you were standing on the surface of this body, you would have no chance in this game. And so this is kind of what the object looks like at the end. And you have all this debris which has been blown off and becomes an important part of the story in how the moon is formed. I have one more movie to show you, which is a more scientific view of this very same process, in which now we're looking at a computer simulation, and we're looking down on the collision from above. So it's as if we're floating above the North Pole and looking down and viewing how this collision takes place. And the nice part about this scientific simulation is that we can actually figure out what the temperatures are when this kind of thing happens. So I'll start it, and then I'll stop it right after the impact. Okay, so what we're seeing here is we're looking down at the North Pole of the impacting bodies. This is horizontal direction, this is vertical direction, and there's a scale here that reflects temperature. The highest temperatures up at the top here are 7,000 degrees. Typically, rocks melt around the blue temperature, around 2,000 degrees. And so what you see here is at the point of impact, you have very, very high temperatures. And watch what happens to the red area as this model evolves. And again, this happens in a matter of hours. So like the movie, what you see is this, the central body is completely covered in an ocean of magma. And all of the debris that's surrounding it is what's referred to as the proto-lunar disk. And it's this material in the proto-lunar disk that will eventually start to coalesce and form the moon. And this material is also all molten. The difference here is that here we have conditions that are very hard to predict. Some people suggest that it's almost equivalent to the vacuum of space, something like a billionth of an atmosphere. But some of these temperatures are so hot that actually the silicate portion of the Earth, the silicon and oxygen, turn from a solid to a liquid into a gas. And so it's thought that actually a silicate, very hot silicate atmosphere might surround this material. So we'll talk about that in a little bit as well. Okay, so lunar volcanic eruptions. These are how we get our samples. But of course, as you just saw, the moon doesn't really start a nice solid body like we see it today. It had a very violent start. And essentially you had an ocean of magma that covered the moon as the little particles and little moonlets coalesced at about the distance where the moon forms. And so it is this cooling of the lunar magma ocean that actually created a lot of the structure that we see on the moon today. So what happens when you have magma that is radiating heat out into space and cooling is that you start to precipitate crystals. And so this is sort of a little cartoon in 3 stages. So time is increasing to the right. This is a little cross-section of the magma ocean. This is a fully molten moon. We don't really know how deep the lunar magma ocean was. But this little cartoon has it molten through the full depth of the moon. So what happens is as this thing cools, you start to form crystals. Minerals called olivine and pyroxene. Corliss talked about some of these minerals in her neighborhood lecture last time. And these minerals are more dense than the magma that they form from, and so they sink. So eventually you create a pile of crystals at the bottom of this magma ocean. And this thing is mixing around too. It's not just sitting still. It's convecting, it's moving around. It's trying to mix these things, but these minerals are so heavy that they sink. But eventually the magma reaches a stage where it saturates in a mineral which is called plagioclase, or a north anorthite. And that mineral floats. And so once the magma starts crystallizing plagioclase, you have plagioclase which is floating to the top of the magma ocean and essentially creating the bright features that you see on the surface of the moon, which are referred to as the lunar highlands. So essentially what you have is a magma ocean that is populated by a whole series of plagioclase rockbergs floating around on top. And this becomes most of the lunar crust. The dark portions of the moon that you see are actually where some of this magma fills impact craters that occur during the moon's impact history. And so this is a fairly complicated scenario for the interior structure of the moon, but it leads to a situation in which we have volcanism that happens on the moon for an extended period of its history. Okay, so we have a plot on the left that essentially shows this volume of magma in the magma ocean and how it's decreasing as a function of time. So it starts around 4.5 billion years ago. We don't know the exact time of the giant impact. We think it was at least within 100 million years of the formation of the solar system. But as the magma ocean cools, its volume decreases, but it doesn't really go to zero. And that's partly because as the magma ocean crystallizes, the magma that's left, little bits of magma that are left, are really, really enriched in heat-producing elements, things like potassium, uranium, and thorium, that heat up their surroundings because of radioactive decay. And so this results in a whole scenario where you can have volcanism happening on the moon long after it's essentially solidified to 99.9%. So a lot of the volcanoes that were active on the moon were erupting anywhere from 4 billion years ago. The main pulse of magnetism happened about 3.5 billion years ago, but it extends even to much younger ages than you see on this diagram. Most of the samples that we'll be talking about were erupted in kind of the 3.5 to 3.8 billion years ago time frame, but a recent paper that was published last year shows that there are even younger features on the surface of the moon that suggest we have magnetism almost to the present day. And these are what are referred to as young magmatic terrains on the moon. They're mapped in various places. There's something like 24 of them here that were mapped out. And what they look like is essentially areas where you have what looks like almost a volcanic crater. And in the floor of the crater, you have these very young-looking features, these kind of bubbly-looking lava flows. And we know that they're young because they have almost no impact craters, only very, very few. And of course, the surrounding is a much older terrain. It has a lot more impact craters. But the method that we use to date the lunar surface based on crater counts and the sizes of craters suggests that these lava flows may have been erupted within the last 100 million years. And so even up to almost the present day, there's parts of the moon that remain hot enough that you can have volcanism reaching the surface. That's pretty interesting. Okay, so again, our samples we'll be talking about are from the main pulse of volcanic activity on the moon at 3.5 to 3.8 billion years ago. Old volcanoes. Volcanoes produce essentially two kinds of deposits. Places like Hawaii, you often have lava flows that create new real estate on the coast of Hawaii and destroy homes, but make new acreage. Those lava flows also cover extensive parts of the moon, especially the low areas where we've had impacts, those dark portions of the moon that you see. But a lesser known type of eruption happens on the moon, which is called a pyroclastic eruption. And this is sort of a picture of a fire fountain from Vesuvius, or this might be Stromboli. I think this is Stromboli, actually in Italy. And in pyroclastic eruptions, you have droplets of magma that are thrown up into the air by the eruption, and they cool in the air before they land on the surface. And so that's why you get these kind of arcing trajectories, and you have particles that are as small as your fingernail up to bowling ball size things that are tossed out in these eruptions. But it's a very, very different scenario on the moon. On the moon, you have 1/6 of the gravity that you have on Earth, and you have no atmosphere to slow these things down. And so a pyroclastic eruption on the moon can toss material for tens of kilometers away from the vent. And these create dark deposits on the moon that are called dark mantle deposits. They've been mapped by numerous lunar missions. They've been mapped on the surface of all the terrestrial planets. So if we ever wanted to get this kind of a sample from another terrestrial planet, would be it Mercury, Venus, or Mars, we would know where to go. So those are the kinds of samples that we study. For the moon, you almost get an aerosol, like a volcanic aerosol that comes out of the vent. And they create glass beads that you see here. So when you have magma that comes out and cools really, really quickly, too quickly enough to form crystals, it will actually form a material that's essentially a glass. So you have what amounts to a magmatic glass. And that's pretty cool. These glasses are really happy things to study in the lab because they really, you don't have to worry about what the original magma composition was and whether you had crystals added to it or subtracted from it. You analyze the glass and you know what the magma composition was. And so these are the objects. The smallest ones are about the diameter of a human hair. The bigger ones are several human hair diameters. And it's these objects that we study and try and understand how the moon formed, how old the volcanoes were, and especially for our purposes, how much water was in the moon's interior. So this is a picture of the ion microprobe that we use to do these measurements. Some of you may have seen it on the campus tour down in the ion microprobe lab. The instrument is essentially a miniature particle accelerator. You make either cesium ions or oxygen ions that sputter the surface of a polished material, and it creates a little crater. And the material that's sputtered out of that crater is analyzed for its chemical composition. And so we have two ion probes, one of which makes what we call big craters. Those might be the diameter of a human hair. And then we have this instrument here, which is called the nanosims, that makes tiny craters. So here we have a cross-section through a lunar glass bead. It's about 300 microns in diameter, so a few human hair diameters. And what we're doing here is measuring the composition of water and other volatile elements like sulfur, chlorine, and fluorine from the center all the way out to the edge. And we're trying to see what's happening to volatiles in these glass beads as they're sort of being ejected from lunar volcanoes and getting ready to land on the lunar surface. And so what you see when you do this is the data diagram on the right side. So what we're looking at, the top panel is water. It's a little hard to see. So the top panel is water. This one's chlorine, this one's fluorine, and this one's sulfur. And this is as a function of distance from the center of the glass bead out to the rim. So water starts out around 30 ppm and drops down to about 10. Chlorine about 0.25 down to about almost nothing. Fluorine is a few ppm, of 8 or 9 ppm down to 4. And sulfur starts at about 200 ppm and drops down to about 150. And what's nice about these 4 elements is that they all move through magma at different speeds. And these speeds have been calibrated to some extent and are continuing to be calibrated in the lab. And so if we know something about those speeds of diffusion and how they are working their way out of the beads, we can say something about the time scale over which this bead formed. So we have to remember that the moon it doesn't have enough gravity to retain an atmosphere. So there's essentially no atmosphere at all on the surface of the moon. The pressure is like a billionth of an atmosphere. And so water wants to go screaming out of this bead. It wants to be in the gas phase. So there's a big chemical gradient that wants to diffuse water through the magma and out the edge of the bead. And it's the same for chlorine, fluorine, and sulfur. And so by doing this, we can understand that in order to match the profiles that we see from the core to the rim, we need a cooling time of about 5 minutes. The other thing that we know about the lunar surface is that it's very cold. And so you would expect this thing to quench to a glass very quickly. But the fact that it requires about 5 minutes to fit these profiles means that there must have been a higher pressure gas cloud that surrounded these eruptions. And in fact, if you look very carefully at the surface of these glass beads, you see precipitates of things like sulfur, like fluorine and chlorine. And so these elements are screaming out of the beads, but then they're recondensing as the whole eruption cloud cools, and these beads sort of settle down on the lunar surface. And so the modeling that we do to try and fit these profiles is sophisticated enough that we tried to make a guess about how much water was in this glass bead actually before it erupted. We were able to do that. And the amount that we get, so the amount that we measure in the center here is about 30 parts per million. We estimated that the bead started with something like 700 or 800 parts per million and lost 95% of its water. Okay, that's a big extrapolation. You know, you're going from 30 ppm to 800 ppm is kind of sticking your neck out a little bit. And so we kind of tried to search for ways that we might use to try and see if this estimate was actually accurate or not. And one of the ways that you can do that is using a type of sample which is called a melt inclusion. And so the top is cut off here a little bit, but what a melt inclusion is it's a little bit of magma, a little bit smaller than the glass beads that we were just looking at, a little bit of magma that's trapped in some of these crystals that grow in the magma while it's cooling. And Edwin Roeder at the U.S. Geological Survey in the 70s pioneered the use of melt inclusions to study volcanic processes on the Earth. He was one of the first people to really look for them in lunar samples when they were returned during the Apollo missions. And so he took a lot of microscope photographs of melt inclusions. At the time that he was doing his work, the particle beam methods to analyze these things didn't exist. And so he speculated that actually these samples would provide some of the best information about volatiles in the moon, but he was not able to really quantify it. One of the things that you might notice is that most of these melt inclusions actually have a little vapor bubble. So you can see a little vapor bubble in this one, you can see one here, there's a vapor bubble in this one. Each of these 3 melt inclusions has a little bubble inside of it. And Edwin Roeder discovered that vapor bubbles can constitute about 1 to 20% of the inclusion by volume. This is one of the observations that led him to suggest that these could be very useful for studying the water content of the moon. And so you can do a very simple back-of-the-envelope calculation. So here you have a melt inclusion which is surrounded by its crystal, And I forgot to mention that the advantage of studying these is that when the sample erupts, the water has no way out of this little bit of magma. It's surrounded by a solid crystal. There's really nowhere for the water to go. And so they're really the best kind of sample to study the volatile content of a magma before it erupts. So if you use the ideal gas equation, you can rearrange this equation to solve for N, which is the number of moles or atoms of gas in the bubble. The P is pressure. You can estimate or take a guess at the pressure. V is volume. It's the volume of the bubble. R is the gas constant. And T is the temperature at which this thing formed. So if you do make a rough estimate of the pressure, let's say 100 bars, which is not very deep below the lunar surface, you can estimate that if you have 1 to 20% of this volume constituted by vapor, you have anywhere from 700 to 13,000 parts per million of volatiles. If it was all carbon, it would be 60 to 1200 ppm. If it was all water, it would be 90 to 1800 ppm. And so, even without doing an analysis here, just making some very simple estimates about what might be in the bubble, we can already tell that lunar magmas have volatiles in them before we even did our first analysis. Okay, but eventually we looked hard enough and we actually found these samples in one of the volcanic glass samples, which is referred to as orange glass. So this is a scanning electron microscope photograph of one of these melt inclusions. It is 30 microns across. It's the diameter of a human hair. You can analyze it pretty easily with the nanosims and get measurements all through this thing. And so the plots on the right are, again, this is a little bit different from the plots we saw before. It's fluorine, sulfur, and chlorine plotted against the water content of the melt inclusions. So each of these dark circles is a single analysis of a melt inclusion. There are something like 6 melt inclusions, but we've analyzed them multiple times. And these light-colored symbols are the glass beads that these things are enclosed in. And so what happens is that the melt inclusions record essentially the water content of the magma before it erupted, anywhere from 500 up to about 1200 ppm. So when we guessed 800, we were actually guessing a little low. These get up to about 1200 ppm. And they correlate, the water contents correlate with the chlorine, correlate with the sulfur, correlate with the fluorine, and point in the direction of the glass beads, which are all highly degassed. And so from this, we were able to actually estimate the water content of the moon's interior. The thing that's interesting here is that the water contents and the chlorine, sulfur, and a little bit like the fluorine actually are in agreement with submarine glasses that are erupted on the global mid-ocean ridge system. So in the oceans, you have volcanoes that are erupting under the seafloor or under the ocean. And it's the pressure of the ocean water that actually keeps volatiles contained in these submarine eruptions. And the fact that the lunar samples agree so closely with these ocean ridge basalts from the Earth suggests that there are parts of the Earth and parts of the moon that have essentially the same water content. So we saw a giant impact that vaporizes not only water and other volatiles, but also even silicate. How does the moon form with this much water in it? It's a real mystery. Okay, so we're going to try and see if we can figure this out. What does it mean for the formation of the moon? It has serious consequences. Okay, so from these measurements of melt inclusions and the glass beads, we are estimating that the water content of the lunar interior that generated these volcanic eruptions is anywhere from 80 to about 400 ppm of water. And that's essentially the same amount as the mantle of the Earth that is in the sort of upper parts of the Earth's interior. So the presence of this amount of water in the lunar mantle is a little bit in conflict with some of these high temperature scenarios that we've been looking at. So how do we get this in? Okay, so we have a diagram here which is essentially a prediction of how much water you would expect in the moon's interior based on that high temperature, giant impact, proto-lunar disk scenario that we just looked at. What we're looking at here is essentially the periodic table almost on one diagram. The horizontal axis is what's referred to as 50% condensation temperature. It's essentially correlated with the vaporization temperature of whatever element you're interested in. So some of the highest temperature elements like tungsten, rhenium, and osmium condense at very, very high temperatures, 1800 degrees. And the vertical axis is essentially our estimate of what the elemental composition of the moon is compared to the Earth. So if we're on a part of the diagram here that's unity, you have a bunch of elements here that are essentially one. It means that for these elements, the moon and the Earth are the same composition. And for the high temperature elements, this is more or less true, except for these elements down here that we think are sequestered in the iron core of the moon. We think that they've followed the core formation process of the moon and have essentially been dragged down into the core. But then you have a dotted line here, which is the prediction of how these elements should behave in a high temperature scenario as a function of their condensation temperature. So for elements that have condensation temperatures that are cooler than about 1,000 degrees, these elements should vaporize during the moon formation process and follow a correlation line that's the same as this dotted line. And you can see that for some elements, things like lithium, boron, sodium, bismuth, iodine, it more or less works. There's some elements like copper and potassium, gold is in there too. But you have a whole host of elements, and especially water, which is at the very cold end of this plot, that really don't fit this line. And so what must have happened is that if the high temperature moon formation scenario is correct, these elements must have been added after the moon formed. So there are essentially 3 steps in the moon's formation that all have different timescales. And we should think about how water might get in or out during these different stages. So the first one we saw was the giant impact stage, where you have essentially impact mass ejection of the Earth's atmosphere. So you have an object which is coming in here and collides with the Earth at a speed of 10 to 15 kilometers per second. You start to make a magma ocean on both bodies, but before this happens, you're essentially blowing off a portion of the Earth's atmosphere. This collision is violent enough that the Earth's atmosphere reaches escape velocity, and away it goes into space, never to come back. This process takes hours to days, and there's really no opportunity for this system to gain water. Okay, so we can rule out that stage in terms of explaining the water content of the moon. Stage 2 is the proto-lunar disk stage. Essentially, in this scenario, which has been being very actively modeled and simulated today, we have the proto-Earth and its magma ocean, and the proto-lunar disk that surrounds the Earth essentially consists of a silicate vapor atmosphere and a thin magma disk at the equator of the Earth. And the size of this disk is essentially anywhere from 2 to 5 or 6 or 7 Earth radii. So it's a pretty extensive size disk. This disk essentially revolves around the Earth. It mixes both horizontally and vertically, and you have exchange of vapor, the silicate vapor cloud, with the thin magma disk, which is condensing. So as this disk cools, you have essentially silicate liquid rain, magma rain, that falls toward the equator and starts to build up a thin magma disk, which is on the order of tens of kilometers in thickness, but many hundreds of kilometers in lateral distance. But of course, this thing is not stable for very long. It will hang together for anywhere from months to about 1 century. About 100 years is about as long as it'll last. And the stuff that is inside the gravitational pull of the Earth will fall back to the Earth. Material in the disk that is far enough away from the Earth that it can sustain its own orbit will coalesce to form the moon. But this process is also very fast, months to centuries, and everything is so hot that the water will either stay in the cloud or will fall back to the Earth. And so some of the most recent models actually have this vapor cloud in a more sort of oval shape around the magma ocean of the Earth and the thin proto-lunar magma disk. So the stuff that's about 2.5 Earth radii away will fall back to the Earth. The stuff that's beyond 2.5 radii will actually coalesce to form the moon. But of course, out here, you don't have very much vapor. The water and the sodium, the potassium, all of the low temperature elements are all in this vapor cloud. And so when the moon starts to condense, there's not a whole lot of vapor around for it to acquire water. And so this stage has very little chance that you actually gain water. And most of the water that goes from the material that forms the moon is essentially being lost from the proto-lunar material. So the last stage is the lunar magma ocean. And the lunar magma ocean, so this is the Earth and its magma ocean with its core. Out here is the moon with its magma ocean and its much smaller core. the lunar magma ocean will start to cool and solidify. And so you have a longer time window. It's not days or weeks or months or even 100 years. The lunar magma ocean takes anywhere from 1 million years to maybe as long as 100 million years to fully solidify. If you wait any longer than that, then the strength of the lunar surface becomes too strong to actually have material reach the depths that you need to produce lunar volcanoes. Impacts will essentially hit the surface of the Earth and stay there. It won't be mixed into the lunar interior. And so you have what geologically is actually a very narrow time window, where you have material which is continuing to fall into both the Earth and the Moon. And this presents an opportunity for hydrous meteorites like carbonaceous chondrites or maybe even comets to impact the Moon, get mixed into the lunar magma ocean, and start to pump up the water content of the lunar interior. And so that's what we think is happening, is that in the latter stages of the Moon's formation, we have material which is falling into the Moon before it creates a crust that's too strong to mix impactor materials into its interior. So that's the story. We have a few acceptable conceptual models for the Moon's formation. I've told you about one, which is essentially the limits of the high temperature formation, but it could be that we're completely wrong about the giant impact. We don't think we are. We think we have a pretty good handle on the fact that there was a magma ocean on the Moon that requires a giant impact. But on the off chance that we're not right about that, there could have been a cold start to the Moon, where the Moon collision creates a protolunar disk that's not actually molten. It's essentially solid. And in that kind of a scenario, you would have no chemical difference between the Earth and the Moon. And so the Moon would look like the Earth in every element, not just water. But there's a lot of evidence that this isn't going to work. You have a possibility of having a warm start, where you have some portion of the protolunar disk that is still solid, about 25% that is essentially Earth composition, and 75% which is degassed of its water. And we think that ultimately, if you add the Moon up in total, we think that it has about a quarter of the water that the Earth had. So this warm start actually would fit the data quite nicely. And then the hot start and equilibration is the one that I was just describing to you, where you have chemical exchange between the Earth and a well-mixed protolunar disk, but the volatiles are determined by the pressure of water at the radius away from the Earth where the Moon forms. It's called the Roche. All right, so that's essentially the tour of what we think about what's happening with water in the lunar interior. And I wanted to, so a hot start and late accretion. This is the model that we were just talking about, where volatiles are added after the lunar magma ocean has started to convect and at the tail end of the planetary accretion. So we think these last three are probably the best scenarios for getting water into the lunar interior. And there's a lot of modeling effort that will begin here fairly shortly at Carnegie to try and understand and see if we can distinguish between these last three scenarios. Okay, so nature abhors a vacuum, and this work is not solely my own. I have a lot of people to thank for this work. But in conclusion, lunar volcanic glasses provide the most direct link to the composition of the lunar interior after the formation of the lunar magma ocean. The water content in the lunar mantle indicates that there are portions of the lunar interior that have the same water content as the Earth. And in terms of the formation models for the Moon, the water in the lunar interior suggests that there's actually a fairly limited extent of volatile for the bulk Moon. It's maybe only about a quarter depleted compared to the Earth. And that models of Moon formation suggest that the water is accreted to the Moon while it's still in a magma ocean state, but before it solidifies. It's clear that we really further work is needed on a whole series of lunar samples to learn more about the origin of the Moon. So these are some of our friends that have helped us to do this. Alberto Saal is my good friend and colleague, many years at Brown University. Mac Rutherford at Brown University. Jim Van Orman, who does a lot of our fancy diffusion modeling and was the first guy to really estimate that maybe some of these water contents were a lot higher before the eruption. And of course in the lab, Jinhua Wang is our longtime rock and anchor in the lab, keeping everything humming. Marianne Lavoie is a recent postdoc who's done some work on lunar samples, and Ben Pandit, who helps us out in the lab also. All of these folks have contributed to the work that you've seen today. Thanks.
Sure, Eric, I'd be happy to answer some questions.
Yeah, go ahead.
The more recent simulations that I've seen in that seem to imply that there wasn't much of the impactor material that was left in the system in the moon and Earth form. That one you showed, there seemed to be more that remained behind. What's the state of that?
Yeah, so the question is, what is the proportion of impactor and proto-Earth that ends up forming the moon? And that has changed a lot in recent years. The sort of canonical collision scenario would result in a moon that's about 75% impactor and only about 25% Earth. But there are new simulations that have been done in which either the Earth is rotating very quickly, or you have a series of collisional parameters that essentially result in about 50-50 Earth and impactor forming the moon. So there's still a lot of detailed geochemical work that's being done to try and understand that, together with a lot of modeling. I think we still don't have the really good idea of the proportion of impactor and proto-Earth in the mixture.
In the back there.
In doing your analysis of the presence of various elements, the hydrogen and oxygen exist independent of water.
Yeah, so the water that we're talking about is essentially hydrogen, but it does, in terms of its mobility, if it's diffusing through the magma or trying to degas, if it's diffusing through the magma, it tends to leave the oxygen behind. And when we speak of degassing of this water, usually it ends up forming, we think, a gas which is essentially molecular hydrogen, H2. We think that the oxygen is essentially left behind in the magma.
This is slightly oblique relative to your talk, related. We know that the moon is receding. What was the position of the moon when this formation took place?
So there is a
How
limit.
many Earth diameters?
Yeah. So there's a limit to the stability of the protolunar disk, which is called the Roche limit,
Right.
which is about 2.5 Earth radii. And so inside that limit, the gravitational pull of the Earth will essentially attempt to break up the disk into little moonlets that are then pulled back into the Earth and accreted back to the Earth. But outside the Roche limit, there's enough angular momentum that actually the orbits of little moonlets that form outside the Roche limit are stable and will not get pulled back into the Earth. And so we think that the moon probably started at the Roche limit and has gradually migrated away
So
over
about
time.
2.5 Earth radius.
Yeah, about 2.5. Yeah.
And what is it at now?
That's a good question. I don't actually know.
About 60.
60? Thanks.
And is the recession rate constant, or did it move more quickly? Or?
I don't think it's been constant. Probably, yes.
Yeah,
I think it's
that's how
slow.
you transfer angular momentum, which is a subject of debate. One of the things that Erik mentioned are these newer models. So one of the issues with the impact models is that they often impart too much angular momentum to the Earth-Moon system. So there is the new models invoke a resonance that transfers that angular momentum to the sun, actually. And there's debate about whether that actually works or not. But the answer to your question is part of this issue about the mechanics of the impact. It's not answered yet.
Yeah, that mechanism for transferring angular momentum to the sun occurs in a very narrow window of parameter space. And so the likelihood about that scenario is actually being actively debated presently.
The question here? You? Yeah.
When the two planets crash, what did they explode?
Yeah, so the reason that you have this violent collision like this is because the things are moving very quickly. So the speed at which these two things hit, 10 to 15 kilometers per second, it's almost like the speed of a gunshot, essentially. So that's a lot of energy that ends up creating all this melt and vapor. It's a very violent event. It's basically the speed of the collision.
I saw a hand up there. Yeah.
Could you just explain angular momentum?
So it's a combination of how far something is from the Earth and its mass. So one of the things that's really characteristic about the Earth-Moon system is the Moon is fairly big compared to the size of the Earth when you look at other planetary moon systems. So, you know, Jupiter has many, many moons. The ratio of the size of the moon to Jupiter is, of course, very small. But there is sort of a characteristic ratio between the size of the satellite and the size of the host planet, if you will. And so the Earth is very unusual in that respect. It has a moon that's really oversized. And so that's why the Earth-Moon system has such a high angular momentum.
So the classic definition of angular momentum is the figure skater. So when a figure skater is spinning and they have their arms out, they're spinning slowly. And then when you tuck in, you spin much faster. That's because of conservation of angular momentum. When you're out there in a distance, you've got energy well out in the radius. When you're like this, you don't have that, so you have to spin up in order to conserve angular momentum.
It's basically the product of mass, velocity, and distance.
Yes, from the center of rotation. Yeah. There was another question up here, yeah? Go in the cap there.
I'm curious whether you said the quantity of water in the crust of the Earth and the Moon is similar. Is it possible to analyze the nature of the water? Is the water, do the isotopes show you whether it's the same? And part B is, was all the water that we have on Earth now already on Earth when the collision took place?
Okay, so yeah, the first part of that is how do the isotopes of the water match up. So hydrogen has two isotopes, hydrogen mass 1 and deuterium mass 2. And the difference is that they both have one proton, but deuterium has a neutron. And so the ratio of these two isotopes can be changed by a lot of processes like evaporation and condensation. And so we did make some measurements of the isotopic composition of the hydrogen in these samples, and they overlap a bit. They don't overlap with an error, but they're fairly close. And both the Moon and the Earth overlap a group of meteorites that are rich in carbon and water. And so it's these meteorites that we think were ultimately the objects that delivered carbon and water and other volatiles to the Moon, but also to the Earth. And so we think that a portion of the Earth's atmosphere was ejected, never to come back. But in this scenario where you create the Moon by giant impact, it's happening at a time when you still have material accreting to both the Earth and the Moon. So the mass of both objects is still increasing a little bit. And so you need a few percent of this material to impact the Earth in order to account for its abundance of water and its isotopic composition. And then you had the second part of your question was
all the water that is on Earth now
right.
on Earth when this took place?
Yeah, we think some of it was lost, and then we got some of it back.
But basically, the
Yeah.
water content of the Earth was huge.
Yeah, it's you know, the whole proto-lunar disk is very hot, and so it's a situation that you would think would be perfect for boiling off water into space. But it's so hot that you have SiO2 molecules in the vapor as well. And so what prevents the water from leaving is collisions with these heavier molecules, and that's really the limiting factor. You have such a dense atmosphere that the water molecules and the hydrogen molecules all collide with all of this SiO2 vapor. And so it actually can be very difficult to lose hydrogen from the system completely. You know, most of it will fall back to the Earth, a little bit of it will be accreted to the Moon, but we need more in the Moon to actually explain our data.
Yep, here.
I'm used to now seeing, I'm glad to see some of these animations. It's fantastic to try to envision how the early Earth was hit by such a big impactor and to create the Moon. But so often I see clouds of rubble left over that, you know, then accretes into the Moon. But, you know, makes sense. But are there any scenarios in which the Earth could have been much more molten and an impact then could have produced something more like a teardrop Moon?
So that's a scenario that has not really been explored extensively. I think most of the people who are simulating these collisions are starting fairly simple, trying to understand the physics in very simple situations, and then if you know, we don't really get the right answer, thinking about the things that are more complex, like successive collisions. There's some work being done on the isotopes of noble gases, things like neon, argon, xenon, that suggests that we have actually, on the Earth, experienced more than one giant impact. There are some models out there, including some models from our own DTM postdoc, Rita Parai, who has suggested that in order to explain the composition of noble gases in the Earth's interior and in the atmosphere, that we need multiple giant impacts, in which each giant impact we lose a little bit of atmosphere and then reaccrete it afterward.
So one last question was back here.
Yeah, I
Yeah,
wanted
go
to
ahead.
ask, how would you, if man wants to go to the moon, what do you have to do to mine the water?
Yeah, so this water is, most of the water that we're looking at has essentially been lost already by the volcanic eruption, except for these little tiny inclusions. And so the pyroclastic glasses that we're looking at do have a lot of elements that might prove useful in a lunar base, in things like metallic elements, sulfur, things that could be pretty interesting and good to mine, titanium. But it's really energetically unfavorable and grossly uneconomic to be able to mine that kind of water. The best shot actually is you have the presence of water ice at the bottoms of lunar craters that are located at the poles. And we think this water was formed by the impact of comets and hydrous meteorites on the lunar surface and migration of water toward the cold traps that are at the poles. Some of these craters are so deep that they never see sunlight. And so that is probably the best chance that we have for extracting useful water on the lunar surface. But those water deposits are probably unrelated to volcanism.
So let's thank Erik again. Thank you all for coming. We hope to see you in the
Thank you.